Good morning everybody, this is Indra. Welcome back to my channel. Today in this video I am going to discuss about one very important application of Laplace transformation. Here we will use the Laplace transformation for the circuit analysis. Here I have taken one example. Please watch this video till the end so that you will be very clear about this example as well as the procedure of how to use the Laplace transformation for the circuit analysis to find the expression for the current and the voltage, etc. And if you don't subscribe my channel yet, please make sure to subscribe it and press the bell icon for instant notification of all the uploaded videos from this channel. Without wasting any further time, let's go ahead. Here, this is the topic of today's discussion, application of the Laplace transformation. First of all, let me read this question. Find the expression for the current I of t. Here the expression for the current is I of t. We have to find out it. And the condition is if the switch is opened at t equals to 0. At the time t equals to 0, the switch is opened in the following circuit. Here the circuit is given here. Before solving this particular question, let me write something about the circuit transformation from time domain to Laplace domain. Equivalent circuit or the circuit transformation. And if there is the capacitor, this is the capacitor. Here this is positive terminal, this is negative terminal. This capacitor, it is in here in the time domain. This is equivalent in the S domain or in the Laplace domain as the here the capacitor is as it is. First the capacitor is as it is, and we have to give the one extra voltage source here in the series. Here one voltage source. This is the equivalent S domain circuit. This is positive, this is negative, and this value, the capacitance will be 1 over Cs. Here the S represents the Laplace domain, and this will be the voltage source will be B0 minus over S, where the B0 minus is the voltage of the capacitor before the time t equals to 0. Here the time t equals to 0 minus, the voltage of the capacitors is B0 minus, and B0 minus over S gives the voltage source here, magnitude of the voltage source. This is the equivalent circuit. Please remember this. This capacitor is changed into this Laplace domain, into this S domain. And similarly, this is 1. And similarly, we can convert the inductor. If the inductor is in the circuit, then we have to convert it into the corresponding S domain. This is positive terminal and this is negative terminal. This is inductor with inductance L, and this is changed into the S domain, corresponding S domain. Let me change here. Here the inductor is as it is, but here extra voltage source. This extra voltage minus and then plus. Here the inductance as it is, and this is the voltage source. And here in the circuit, the I of S will flow current in the S domain, and here also the I of S will flow in the circuit. And here this has the value, this inductance has the value. What will be the value? This is Ls, and this voltage source will be, the value of the voltage source will be L I0 minus, where the I0 minus is the current flowing through the inductor before the time t equals to 0. Here, please memorize these equivalent circuits in the S domain. These are the equivalent circuits of capacitor and the inductor in the corresponding S domain or Laplace domain. Let's solve this particular question by using this concept. Here, first of all, here let's find out here the both capacitor and the inductor. Here the inductor and the capacitor are used. So first of all, finding out B of 0 minus and I of 0 minus. So when t equals to 0 minus, let me draw the circuit corresponding equivalent circuit. This means here the switch is opened at t equals to 0. Here the at t equals to 0, switch is open, and the before the switch open, the switch was closed. Switch was closed at time t equals to 0 minus. So let me draw the corresponding circuit here. The switch is closed here. This is the position of switch. And let me draw. This is the voltage source, plus minus as it is. And here at t equals to 0 minus, please memorize this. At t equals to 0 minus, the resistance will be the same. But the inductor behaves is the t equals to 0 minus. When the t equals to 0 minus, it behaves as the final position, final state. And at the final state, the inductor will be the short circuit. Please memorize this. The inductor will be the short circuit when t equals to 0 minus. And similarly, we can draw here the resistance will be the as it is, and the capacitor when t equals to 0 minus, the capacitor will be the open circuit. Here this is the open circuit, the capacitor, and here this is the short circuit in the inductor. And let's find out here the voltage across the capacitor is be 0 minus at t equals to 0 minus, and here this current flowing through this inductor is just I 0 minus when time t equals to 0 minus. Let's find out the value of B 0 minus and I 0 minus. Here in this circuit, in this loop, in this first loop, let's use the Kirchhoff's voltage law, KVL, and here it has the value 2 volt as it is 2 volt. And if we use the Kirchhoff's voltage law here, 2 times I 0 minus is here equals to 2 volt. Therefore, the value of the I 0 minus will be just 2 over 2. This will be 1 ampere. Here we have calculated the current flowing through the inductor when the t equals to 0 minus is here as a 1 ampere. This is one requirement. We need I0 minus and B0 minus. And let's do the calculation for the B0 minus. And here the B0 minus is the voltage across this capacitor when the t equals to 0 minus. And this voltage, here the current flowing through this circuit. Here the current flowing through this circuit is here calculated as the 1 ampere in this circuit, and here the open circuit, so that there will be the no current. This will be the voltage is 0. Here its corresponding voltage is 0. So the voltage of this should be the same as the voltage of this, because they are in the parallel. So the B0 minus will be same as the voltage across this terminal. Voltage across this terminal is just 2 times 1 gives 2 volt. This is just 2 volt. Here we have calculated B0 minus is the 2 volt. Value of the B0 minus is just 2 volt by using the Kirchhoff's law. The first step is to calculate the B0 minus and I0 minus. And the second step, this is the first step. Let me write, this is the first step number 1. And let's move to the next step. Next step is step 2. And the next step is just transforming this circuit of the capacitors and the inductor by the Laplace domain, by the S domain. And let when the switch is open, when the t equals to 0 plus, when the here at these situations the switch will be the opened at t equals to 0 plus, and the corresponding circuit will be this will be the open circuit. Let me draw 1 second. This is just plus minus. This is 2 volt. Let's draw the corresponding circuit. And this is the resistance will be the same. Resistance will be the same, and in place of the inductor, we have to insert this circuit. This is the corresponding inductor circuit in the S domain. Let's insert here. The inductor will be the same as it is, and here the minus plus. Let me draw the complete circuit. This is just 2 ohm, and the this is just Ls, and this will be just L times I of 0 minus. And the next here, the next part is this one, just replacing this capacitor by this circuit. And here is also the resistance 2 ohm, and in place of the capacitor, in place of this capacitor, we have to insert this circuit. Let's insert. The capacitance will be the as it is, and this will be plus minus. This is voltage source. This is the equivalent circuit, and here this voltage source will be V0 minus over S, and this capacitance will be 1 over CS, and this is Ls, and this is L times I0. Here the value of V0 minus and the I0 minus are calculated here, and let's use the KVL here. This is the open circuit. So this region is useless. This part is useless part. Here the open circuit, there will be no current flow through it. And let's evaluate here. Let's use the in this circuit, in this loop, let's use the Kirchhoff's voltage law here. And here this is minus, this is plus, this is minus, this is plus, this is plus minus, plus minus, plus minus, plus minus. Here let's use the KVL in this loop. Here the KVL, applying the KVL in this loop, in this closed loop. And the KVL, let's apply the KVL here. The L times I0 minus, this is L times I0 minus. Let's assume the direction of the current here. Here the current is flowing. Here the current is flowing in these directions. So this will be the direction of the current. This is the direction of the current. And let's use this. And here, from here, let's evaluate the corresponding value. This will be, here the current is flowing, this will be negative. Here I am going to just use the KVL. This KVL. This is negative L I of 0 minus. And let's move here. And this will be negative B 0 minus over S. This will be positive 1 over CS times I of S. Here in this case the I of S current will be I of S. I of S current will flow here. And plus 2 times I of S plus 2 times I of S plus here the voltage across this inductor is just Ls times I of S. And this will be the net voltage, will be the sum of the net voltage will be the 0. This is the KVL. This is the expression after applying the KVL. Let's plug in the value. Here the I of 0 is just 1, negative L. L is here, where is the inductor value? Inductance is here 1 Henry. So this will be the negative 1. This will be negative 1 minus, and the B0 minus is just here 2 volt. So this will be 2 over S plus, and the capacitance, here the capacitance is 1/4. This is the value of the C. If we plug in the value of the C, this will be 4 over S, I of s plus 2 I of s plus this is 2 I of s plus here the inductor is just 1 times L of s, and this is just s I of s. This is equals to 0. First of all, let's evaluate the value of the I of s. From these expressions, the value of the I of s, let me write it directly here. I of s will be just 1 plus 2 over s all over this term 4 over s plus this will be 2 plus 2 will be 4 plus s. Let's simplify this expression, and this will be just 2 plus s over, if we simplify this will be s square plus 4s plus 4, and this can be further simplified as here. This can be written, this expression in the denominator can be written in the perfect square as the s plus 2 whole square. This is just s plus 2 whole square, and here the s plus 2 in the numerator. So finally we obtain 1 over s plus 2. This is the value of the I of s. Here we finally obtain the expression for the I of s. It is in the s domain, and we need here by the question we need into the time domain. We need in the time domain, so we have to use the inverse Laplace transform here. So finally we have obtained I of s is this expression. Let me write here. Here the I of s is obtained here just 1 over s plus 2. Let's use the inverse Laplace. This is the inverse Laplace transform of this expression 1 over s plus 2. Inverse Laplace transform of this is just, here the number is 1 times e to the power, here the s plus 2, here the plus, so we have to minus, and here the number is 2, so 2t. This is the final expression for the current. Therefore it is the expression of current I of t in the time domain. Here we finally obtain I of t, current in the time domain. I of t expression for the current is just e to the power negative 2t. It is the required answer of this question. In our next video, we will discuss more about such type of the applications of the Laplace transformation in the electrical circuit analysis. Please keep watching, keep loving this channel, and don't forget to subscribe this. We will meet in our next video. This much for today. Thank you.